5.4 kilogram box sliding down a 5.1 meter high frictionless hill starting from rest. It then slides across a 2.1 meter long horizontal surface, then hits a horizontal spring. The spring has a spring constant of 520 newtons per meter. The other end of the spring is attached to anchored against a wall. The ground under the spring is frictionless, but the 2.1 meter long segment is rough, meaning it has friction. Coefficient of kinetic friction between the block and that surface will be 0.27. How far is the spring compressed? So energy. You can use energy in whichever form you like. We had work is equal to the change in potential energy plus the change in kinetic energy. There will be work done by friction at some point during this process. You can also use it as energy initial plus the work done equals the energy finals. Either way, it's the same equation. So initially, I'm going to take my initial point up here. And I'm going to put my final point down here where the mass has compressed the spring some distance x. So initially, what type of energy does my system have? Potential. Elastic or gravitational? Gravitational. So the amount of energy it has will depend upon the mass of our object, acceleration of gravity, and the initial height. We know the initial height, we know the mass, we know g. Kinetic energy is 0 because it was released from rest, so it's not moving at that instant. Finally, there will be potential energy, but now it's elastic potential energy because the spring is compressed. There's no gravitational potential energy since we're saying that the ground level is y equals 0. The kinetic energy down here is 0 because at that instant when it has compressed the spring as far as it can, it will have come to rest. Now granted, the spring's going to push it back out and it would head backwards through its path. But that's irrelevant to answering this question. So we have two pieces of our information. We now need work. If there's any forces outside of gravity or the spring that are causing the object to speed up or slow down, you have to figure out how much work is done by them. Since friction is the one doing work, we have a force of friction in this segment down here. The force of friction is constant, so the work done by friction will simply be the force dotted with the displacement. Since the force will be opposite the displacement, work's going to be negative. The force of friction is simply the coefficient of kinetic friction times the normal force. Conveniently, this is a horizontal surface. The normal force will equal the force of gravity in this case. So normal force will be mg. Then we need to multiply by the distance that friction acts over. So that 2.1 meters is our distance d. Please watch your units. A lot of you would realize that you accidentally left the d off if you watch your units. This term, work, what units does work have to have? Joules, which is a Newton times a meter. So if you watch your units, make sure you're coming up with Newtons times meters. Okay, so either way, we can use this one or this one. They're equivalent. If we use this one, all of the initial energy we start with, in this case is just mgy, plus whatever work is done. Well, the work done is negative mu mgd. That's the work done. That has to equal the final energy we have, which is, in this case, 1/2 kx squared. Keep in mind that work needs to be on the initial side. It needs to be with the initial information. Whatever energy you're starting with, work is taking away in this case. Friction is doing work. It's taking energy away from the initial value that we had. That's why it needs to be on the initial side. So our mass was 5.4 kilograms. G is 9.8 meters per second squared. Y initial was 5.1 meters. Mu is 0.27. M is 5.4. G is 9.8. D is 2.1. Divide that by 1/2 of K. Square root it. That will be our X value. X ends up being 0.96 meters. So of course we're assuming the spring has enough room to compress that far. Now I know some of you broke it into pieces. You found the speed at the bottom and then looked at kinetic energy right at the bottom of the hill to right before the spring, which is fine. There's nothing wrong with breaking it in pieces. You don't have to, but